Hi, I'm Sebastian,
I'm Austin.
and we're here to present a reading group on deep kernel learning. So as a brief outline of the talk, in this reading group, we're going to discuss, first of all, some motivation and background, which will include neural networks and Gaussian processes. And then we'll discuss a bit what is deep kernel learning. And then Austin will come and discuss about some recent advances and insights about deep kernel learning. And then also, which includes shortcomings and addressing these shortcomings. So first for motivation and background. So in terms of neural networks, these have been really popular recently. And they're great for high dimensional tasks such as images, NLP, everything like that. And the way they're often framed to work is that they learn useful features from the data. And then recent advances also mean, recent being the past 5 or 10 years, mean that they can be trained very straightforwardly. However, they have a tendency to be overconfident. This is quite well documented in the past 5 or so years. And uncertainty representation is difficult. There are millions of parameters, and from a Bayesian point of view, inferring posterior distributions over these parameters is notoriously tricky. And finally, we would want good uncertainty for many tasks. Autonomous driving, medical tasks, these are always claimed as tasks that we would want good uncertainty for neural networks. So briefly on the importance of learning features. So learning features from the data are really an essential part. They've really been found to be an essential part of achieving good performance, particularly for high dimensional tasks. And here we have a plot from a paper by Greg Yang and Hu, in which many of you may be aware of the neural tangent kernel. If you're not, it's not that important for this talk. But that's essentially an infinite width neural network. And when you train it, you can show that you're actually not really learning any features. So here we have a classification problem, and we can see what happens sort of with the features that you get on this two-class classification problem. And for the NTK, where you don't learn features, you see that the classes are all kind of jumbled together. There's no clear separation. However, for a finite width neural network, which does learn features, we see that the classes are quite well separated. And then the point of Greg Yang's paper was to show that you can find an infinite width limit where you do learn features, but that's really an aside, and that's on the right-hand side. But essentially, you want to learn features which in classification basically discriminate the task for you so that you can just apply a feature extractor on the last layer. Andrew, you have a question?
Can this also extract feature here?
This is just like a representation of the last layer features.
Okay.
Like I think a PCA or something. Okay, so those are briefly neural networks. Now, on the other hand, we have Gaussian processes, which are great for representing uncertainty. So a definition of a Gaussian process is that a Gaussian process is defined as a collection of random variables indexed by a set X, such that any finite collection of these random variables is jointly Gaussian. And that might not appear to be too useful immediately, but in fact, we get a lot of useful properties. We can specify, for instance, a GP entirely with a mean function M and a covariance function K. And here I put K theta because you might have some learnable hyperparameters, as we'll see a bit later. And we can show that, all you need is this mean and covariance to define what your Gaussian process is. And even more useful for closed form, for regression, we have closed form expressions for the predictions. So that's your posterior predictive at a new test point, given your data X train and Y train. And we're also conditioning on the hyperparameters here. And we also get a closed form expression for the marginal likelihood, which is just the probability of the data given your hyperparameters. Now, as a quick example, a popular choice of kernel is the squared exponential kernel or radial basis function. And here we can see two plots. On the left, we've got a plot of the prior, and on the right, we've got a plot of a posterior condition on points, on data points. And essentially, you can see that the radial basis function kernel encodes a very smooth function. And yeah, you get this nice conditioning, which is you can compute this all in closed form basically, and it's very nice to deal with. Now, how do we learn for Gaussian how do we learn with Gaussian processes? Well, GPs are non-parametric models, and learning involves fitting these hyperparameters that I mentioned. So your kernel parameter is theta. So an example for the radial basis function, we have a signal variant sigma f, and then we have a length scale L, and then also a noise variant sigma n. And here we've got a plots of fits given different values of these hyperparameters, as particularly the length scale. And we see for length scale 1 on the left, we get quite a nice fit of the data. Length scale, a small length scale though, will tend to really overfit and give you very complicated fits, whereas a larger length scale will tend to underfit the data and not really give you the definition you want in your fit. So it's actually really quite crucial to learn these hyperparameters in some way or another. So there are a few strategies for learning. The first one is to do full Bayesian inference, where we introduce a hyperprior P of theta and calculate a hyperposterior P of theta given your data. Now, this can't be done in closed form, so you have to resort to some approximate method, and so it can quickly get quite expensive. On the other hand, we have empirical Bayes, which is maximum marginal likelihood, type 2 maximum likelihood. And this is just, you find a reasonable point estimate of theta by maximizing your marginal likelihood, P of y given x and theta. And this is where GPs really shine, because you can find this marginal likelihood in regression, at least in closed form. And so, and that becomes, you can show that it sort of results in a complexity penalty term and a data fit term. And this is actually up to a constant term. It's missing a term of like log 2 pi. So essentially what the marginal likelihood tells you here is that you've got a trade-off between the complexity and the data fit. And for instance, in the previous slide, we saw that a small length scale could fit the data really well, but that'll actually get penalized quite heavily with the complexity penalty. Whereas a larger length scale might not fit the data as well, it will underfit. But it'll have a good complexity. So you've got this trade-off where sort of larger length scales will do better in terms of the complexity penalty, and smaller length scales would do better in terms of the data fit. So the rationale for empirical Bayes is essentially that you get an automatic trade-off between data fit and complexity. Now, as another issue with Gaussian processes, they have kind of notoriously poor scaling. So it's in terms of the data set, if you have n data points, you'll have cubic computational cost and quadratic memory cost. And the way this is often addressed nowadays is through stochastic variational inference via Hensman. And what we do here is we consider m inducing points, inducing location z, and some corresponding inducing variables u. And we form an approximate posterior, which we then learn, which is usually QU being a normal distribution with mean m and covariance s. And m and s are learned variational parameters. And given this, we can derive an evidence lower bound for the approximate posterior. We use the QU to condition f. And so with this form of approximate posterior, we can show that the elbow is given by an expected log likelihood term under Q of f minus a KL between QU and your prior U. And this kind of mirrors the way that the marginal likelihood works, right? You've got a data fit term here on the left, and you've kind of got a complexity penalty on the right. And for regression, you can show that there are quite close similarities between the two. And so we use this evidence lower bound, the elbow, to learn your variational parameters, which in this case are z, the inducing locations, m and s, the variational parameters of the approximating posterior. And we can also use this to learn hyperparameters theta, because actually this is quite a close bound to the marginal likelihood. And this can reduce the computational complexity to, for one epoch of training, to order m squared n. So that's sort of addressing how we train Gaussian processes and the computational complexity issues. Now I'm going to talk about kernel design, because for typical kernels with Gaussian processes, they tend to be fixed and you don't actually learn the features. For instance, with the squared exponential kernel, you do have features which are tunable. You can change the length scale, which changes the effective features you get, but the features themselves are not learned, unlike with a neural network. So there's been quite a, Andrew?
What do you mean by features in this case? Are you thinking about like an eigenfunction expansion, or are you saying something else?
So you can look at it many ways. There's like the canonical features for like, which are just essentially Gaussians. And if you've got an infinite number of those, you get the squared exponential function. That's more what I was referring to in this case. So, and in the past, 10 years or so, there's been a lot of attempts to really try to get better kernels, learn better kernels. So there are quite a few attempts that try to use combinations of simple kernels, such as adding kernels, multiplying kernels. And this adding and multiplying kernels, you can show quite straightforwardly, still gives you a valid kernel function. So there's the automatic statistician, there's the neural kernel network, and very recently there was this work called KIT, which uses transformers to predict kernels for a data set. And so, for instance, up here I've shown a plot from the neural kernel network paper, and you can see that the kernel learned is actually is quite an interesting function. So you can do some quite cool things with these approaches, but it can be a bit complicated with, how do you choose how to formulate these combinations? How do you choose which kernel is the best? On the other hand, there's work trying to directly formulate more flexible kernels, such as the spectral mixture kernel. There's work called functional kernel learning quite recently. And Finally, there's also a line of work on deep Gaussian processes, which essentially tries to avoid this issue entirely by just using compositions of Gaussian processes, which you can kind of view as leading to more flexible effective kernels. Like, you don't directly encode a more flexible kernel, you let the model try to figure that out for you. But is there a simpler way? And this leads us to deep kernel learning. And so deep kernel learning methods use a neural network to transform the inputs to the Gaussian process. And it's very simple. You have a neural network and you just replace the kernel. You have your base kernel, like a squared exponential, and then you just put the inputs directly into your neural network and then into the kernel. And this is essentially all that these deep kernel learning methods try to do. And so just to be clear, we have parameters theta for the base kernel and parameters phi for the neural network. And it's quite easy to show that the resulting kernel is still a valid kernel, so we're all good there. And the marginal likelihood can be computed in the exact same way as previously. You form your gram matrix with the data points, and you can just compute it straightforwardly. So the big question then is, how do we train this model? Because now we have a neural network in the mix. So on this slide, I'll briefly go through how do we train deep kernel learning models, and this will kind of include a bit of a brief history lesson on deep kernel learning methods. So the first paper that I'm aware of that tries to do something like this, is by Hinton and Salakutdinov. Apologies if I butchered that. And they pre-trained the neural network using unsupervised learning. They use essentially an extension of restricted Boltzmann machines. And then they showed that you can fine-tune this using the marginal likelihood. Later then, Calandra et al., they trained the model end-to-end using the marginal likelihood. And so they skip the pre-training compute completely. They work entirely with the marginal likelihood. They don't do any sparse inference, any variational inference, and they just use regression, so it's quite straightforward. But they do note some potential issues with overfitting. They do mention, for instance, that the neural network shouldn't be made too large. Then Wilson et al. Later, they used KISS-GP, which is a separate way to obtain scalable GPs. I won't go into the details there. And then they did a very similar thing. They used KISS-GP with regression, and they called the result deep kernel learning. So this was the first paper to actually use the term deep kernel learning. And I should point out that like technically deep kernel learning does really only refer to this method, but it's the term that seems to have caught on. So we're going to abuse the notation a bit and just call everything that sort of tries something like this deep kernel learning. And then later, Wilson also used SVI in this, similar to the Hensman method, to extend this model to non-Gaussian likelihoods. So they showed some classification results. They used some Toeplitz structure with a more complicated model with many independent GPs and then a mixing matrix to further reduce the computational complexity. And here they note that they had to use pre-training of the neural network and then some fine-tuning afterwards to get it to work well. And then finally, Bradshaw et al. Use a bit of a simpler model with sort of more standard stochastic variational inference for GPs. And they really found that for the bigger models, for the more complex data sets, pre-training was necessary to achieve good performance. Andrew?
Sorry, you might have already mentioned this, but in the more recent pre-training, what kind of things do they do? Presumably not RDMs, right?
No, they just use a neural network trained with a classification loss, so cross entropy loss.
So that's what we do with the marginal likelihood during the pre-training stage.
No, they in the later ones they just do standard deterministic training of the neural networks. Okay, and really briefly, here are some empirical results from these papers. So the first thing to show is that on the left here we have this function which is clearly just a step function, and on the right we have something very similar where the true data is created with multiple step functions. And so in the blue, we have a GP with sort of squared exponential kernel. And then we have the dotted line here is a GP with a neural network in the kernel, but it's not being trained with the marginal likelihood. It's just being trained entirely deterministically and then fixed before you put it into the GP. And then this paper was the Calandra paper, so they called it manifold GP. This was the deep kernel learning method where you do train with the marginal likelihood. And essentially you see that the squared exponential kernel isn't really able to handle the step function very well. Whereas the neural network kernel one and then the deep kernel learning one do a lot better in handling the step function. And they argue here that the deep kernel learning one generalizes a lot better because it kind of stays flat outside this region where there's data. Whereas the GPNN one kind of returns more to the mean function. And on the right here, you see that, yes, Rich?
At a counterpoint, the other way of viewing the green dotted line is the manifold GP. It looks like overfitted to me.
Yeah, you could argue that. Yeah, I would probably actually agree with that assessment. Yeah, there's very little.
There's only way to continue that.
Yeah, exactly.
Step function which alters our inductive bias, but of course the neural network doesn't know anything about that, so it could step up, it could step down.
Yeah, no, I kind of agree with you there. And yeah, so then here on the right, we again see we've got a few different kernels. We've got the squared exponential kernel, which is in blue. Then we've got this spectral mixture kernel, and then we've got deep kernel learning. And you see that only the deep kernel learning is able to handle these very sharp transitions. So it is much more flexible than these other kernels. And this squared exponential kernel seems to fail really catastrophically for some reason on this. And then finally below here, we've got some classification examples, and the columns I would draw your attention to are the CNN, CNN plus GP, and then the stochastic variational deep kernel learning. And we see basically that the deep kernel learning method performs the best out of all of these, and it consistently does improve over the just the base CNN in terms of accuracy, and this is before you even get to any uncertainty gains. So you can consistently improve just by training an additional GP on top what you get out of neural network. Andrew?
How CNN plus GP trained? Is it using an elbow, or is it treating classification progression, or
CNN plus GP is the exact same as the SVDKL, as far as I understand it and remember it, is the same as the SVDKL model, except when you train, you don't update the neural network weights. So you have to do this pre-training step here, where you pre-train the neural network deterministically, and then you have, and then for the CNN plus GP, they just add the GP on top, train the GP parameters, whereas for the SVDKL, they train everything jointly.
Okay, but all the models of GPs use the elbow to handle, like, you know.
Yeah.
Maybe, I'm not sure, maybe you're going to return to this, so
yeah.
It might be not helpful in terms of your pedagogy of the presentation, but so my feeling here is you have to be we have to be quite clear about what game we're trying to play here. Like, what's our real task that we're after? Are we trying to scale this to ImageNet or something, serious? And in the context, if you are going to go after a proper computer vision application and you want to get joint uncertainty right in that space with that active learning, then pre-training seems totally fine to me. Like having the pre-trained network and downloading it and then building a GPU on top and not touching any more network seems like it would, in general, be completely adequate. But maybe a bit of fine-tuning, and that would even play better because we know that we've now got some massive parametric model. There's a non-parametric bit, but there's like a thin slice of non-parametric stuff on the top, and then bazillions of parameters underneath. It's basically a parametric model.
Yeah.
So it will overfit, even if we're using VR.
Yeah, so we're going to touch on that a bit. Austin will come and talk about that a bit later, some things related to that.
So the narrative here that joint training is going to be better versus end-to-end learning is better. It doesn't really sit very easy to me, both from the practical perspective and from the empirical performance perspective. It's not what people do in computer vision most of the time, and we're going to overfit if we do that anyway. Yeah,
I agree with pretty much everything you said there. I guess the point these papers are trying to make is that it's not just because you've slapped a GP on top that you're getting better performance. It's like you get the best performance when you train everything jointly. Sorry, maybe that wasn't quite that wasn't a great answer, but like basically they're trying to argue that you should train everything jointly afterwards, and you don't just want to put a GP on top of a pre-train.
I agree, that's what they're saying, and I guess they're saying that's not necessarily the case, especially in the direction where you're heading with these methods.
Yeah, sure. Yeah. No, we'll get to that later, hopefully. But yeah. Elrie?
We've had a request from the Zoom audience to please repeat the questions before you answer them.
Oh, I see.
It's tricky to hear.
Yeah. Okay. I guess so. Rich was asking, should I do this now or just later?
Difficult discussion to repeat.
Okay. We'll bear that in mind for future questions. So in summary, what is deep kernel learning? Well, deep kernel learning methods essentially attempt to combine the feature representation capabilities of neural networks with the uncertainty of Gaussian processes in a straightforward way. That means we don't have to try to do posterior inference over everything. And they do this by transforming the inputs using a learned neural network to learn good features that a GP model can then use. And it has shown success in regression, classification. There are papers on time series with deep kernel learning and a bunch more applications. And yeah, there is some evidence in the literature that deep kernel learning models can be hard to train, for instance, requiring the pre-training. And there are some warnings about overfitting. And basically in the following slides, Austin will go through some of the more recent insights and advances in the deep kernel learning methods, which kind of address this latter point. All right, so I'll hand over to Austin now.
Hi everyone. So this next section should be quite pleasing to Rich because it's essentially just addressing the discussion we had earlier. Apologies for those of you online who didn't really hear the question clearly. So as alluded to earlier, a persistent problem in deep kernel learning is overfitting. It's maybe not super surprising the way Rich put it, that if you have a model with a huge number of parameters and a small non-parametric on top, it's sort of like a parametric model, and then you might overfit. And we can sort of see this in practice. In this section, actually, one paper I'm going to talk about is Sebastian's paper from this year, which has a really good illustration of this. So they use a simple 1D toy data set with 200 points. It's actually visualized below, just wait a few animations. They do a really simple deep kernel learning model. So as a feature extractor, they have like a 3-layer network, a few hundred neurons in each layer, and then they use an exact GP on top with an RBF kernel, I think. They train it just by maximizing the marginal likelihood. Everything's trained jointly. It's a simple 1D data set, so they don't, I think, really need any pre-training. And the result is actually that it really does quite poorly. It overfits significantly. The exact result you see here is on the left. So in the region of the data, which are these red dots here, it fits fairly well. The mean goes through, the uncertainty is fairly small. And then outside of the data, where you expect it to revert to some sort of prior and have low, like a high uncertainty rather. It does the exact opposite. It makes these extreme predictions, and it has very low uncertainty about these extreme predictions. This seems like a very classic case of overfitting. It's good to contrast this with something that behaves a lot more like we want to, which is shown in figure B here. That's just a non-deep kernel learning GP with just an RBF kernel where we learn the length scale of noise parameters, etc. And what we see is that in the region of the data, it does sort of what we want. The mean goes through the data points, the predictive variance is rather small, and then outside the data, the predictive mean reverts to the prior mean, so it's not making some strange prediction with no evidence, and the uncertainty is quite high. So the difference between using the GP and using the GP with this extra feature extractor is that the performance actually goes down quite a bit. If we do the other way and not instead of discarding the feature extractor, discard the GP, we get what's shown here in figure C, where you just see the result of fitting a neural network with no uncertainty. And arguably, even it does a better job than the deep kernel learning. So in the region of the data, as you might expect, the prediction goes roughly through the data. So I think pretty good. And then outside of it, it essentially predicts 0 or something close to the data set mean, which is probably better in some sense than predicting extreme values like deep kernel learning does. Of course, there's no uncertainty because it's not a Bayesian neural network, there's no GP attached, but arguably you could say that even adding this extra GP, which is supposed to give it uncertainty and make it better, has actually made it worse. And to top this all off, if you look in plot D here, this is just showing some training curves for the deep kernel learning. And what you see is some behavior that you might not like to see when you're training anything with 30%. You see these very huge fluctuations in the marginal likelihood. And between different runs, which are shown in different colors here, you see that the performance actually varies quite a bit. So there's a lot of variance, and it seems to be kind of inconsistent, a bit unstable. So even in this toy example, it's just not doing that very well. And that's a bit concerning, because if you have a method that fails pretty spectacularly on a simple toy example, it might not give you hope that it's going to do well in practice for real problems. Although it's interesting to note, this is sort of in conflict with what we saw previously, where it actually was able to do decently on actual more challenging tasks like CIFAR 10 without at least like overfitting so spectacularly that it got like a poor test accuracy. So the remaining part of Sebastian's paper really is going through this and trying to work out like what exactly is causing the overfitting and why don't we see it more in the previous papers which reported good results, or they were able to overcome overfitting. So the main claim made in this paper is that the overfitting is due to the complexity penalty. So in the bottom right here, I've shown you the marginal likelihood just to remind everyone, and it has two terms. Remember this complexity term, which is essentially the log determinant of the kernel matrix, and the data fit term, which is essentially the mean squared error. So the theorem is actually shown in this paper is that if your kernel has like a learnable output scale parameter, that is to say that it's equal to some learnable scale, like non-negative scale parameter times some base kernel, then when you optimize this and you choose the optimal output scale, your data fit term will actually always equal n/2. This might be a very weird or unintuitive result, but it turns out that if you just take the derivative of this marginal likelihood with respect to this sigma squared f parameter and do some math and substitution, you actually get n/2 popping out of that, which is kind of shocking and interesting. At least I was kind of surprised by it. And of course, they validate this empirically on the same toy data set that we saw in the previous slide. If you just look here, if you break up the data fit term, maybe it's a little small to see, but it essentially levels out at exactly -100. And if you recall, there were 200 data points, so that's n/2. Check. And that means that all the differences between the runs are actually coming from the complexity term. And you see that actually varies reasonably significantly between the different runs. So overall, I guess what this is showing then is that if we want to look at what's going wrong with deep kernel learning, we should be looking at the complexity term, not the data fit term. So then let's take a closer look at the complexity penalty. As shown in the previous slide, the penalty has this form. It's -0.5 times the log of the absolute value of the determinant, although you don't need the absolute value because it's always going to be positive. The kernel matrix has to be a positive semi-definite matrix. What does this imply? Well, this implies that the kernel matrix should have a small determinant, because if you're maximizing this objective, you want the number going to the log to be a small number so that it's as high as possible. A small determinant for for any matrix with strictly positive eigenvalues means that it effectively has to have small eigenvalues. And small eigenvalues can be interpreted as the matrix, well, at least one way to interpret it is that the matrix will be approximately equivalent to a low rank matrix. And if you think about what the entries in the kernel matrix mean, it's that if you can approximate it as just approximate it quite accurately with a low rank, it means that you actually have quite a lot of correlation between the points, as in there's a lot of redundancy in the matrix. So the prediction then is that if it's overfitting, the way the overfitting works is by introducing as much correlation between as many points as possible so that you get low eigenvalues in an approximately low rank kernel matrix. And this seems to be in practice what is observed. So this is a replication of the two plots from the previous slide. So in the left plot, you see the squared exponential kernel, the one that had a pretty good fit. And in the bottom here, what's plotted is the kernel function, which is with one argument fixed. So the red argument has, or the red line, sorry, has the x argument fixed at that red line at the right, and then the black curve has the one argument fixed at the black line on the left. And then the second argument is allowed to vary, and what you see is how the correlation varies. So for the squared exponential kernel, maybe it's actually easier if I go up here and point it out. So the squared exponential kernel, you see that the variance, or sorry, the correlation is decaying quite neatly as you go away from the central point. For both points that they looked at in the domain, that's sort of what you expect. And with deep kernel learning, this doesn't happen. If you look at the correlation is essentially constant. There's some small variations, but it's essentially constant, meaning that within this domain, like all points are approximately equally correlated to all other points. So that's bad. And that's and in this, at least in this 1D case, that seems to be a very clear explanation of why this hasn't worked. And you'd think that if you have something like, instead of a 3-layer feature extractor, you have some huge ResNet and you have a huge image data set, that you might get the same thing, but only worse. Yet, again, in practice, people have observed that somehow this doesn't always happen. It can happen, but it seems to be like avoidable in practice. So in his paper, and in 2 other papers I'll talk about, they talk about some strategies or to, I guess, either intentionally or accidentally avoid overfitting. So the first observation actually that's made in Sebastian's paper is that if instead of using an exact GP, you use a stochastic variational GP, these overfitting problems in practice occur much less often. And the reason that they propose is that because with stochastic or variational GPs, at least this formulation is the stochastic variational GP, you can train with mini batches. So you use stochastic gradient descent rather than full batch gradient descent. And this means that the model never sees the full data set at any one time, and therefore it makes it more difficult to correlate all points to each other. In practice, this seems to make overfitting occur much less frequently. In his paper, they do a lot of experiments with the same model replacing sort of with different batch sizes with full batch gradient descent versus mini batch gradient descent. But the result essentially is that using mini batches seems to really effectively combat this overfitting. And this is why they theorize that these previous papers, despite not having any really principled reason why they shouldn't overfit, in practice report results that suggest that they didn't overfit. A second strategy that that's mentioned in Sebastian's paper is, rather than using this empirical Bayes strategy, just be full Bayesian. And it would kind of be intuitively sensible why that would prevent overfitting, because you're not going to find some particular value of the hyperparameters where everything's correlated. And I think with the toy example and with, I think, one other example, they do like full they do full Bayesian inference. I think they use HMC, if I remember correctly, and they show that this results in significantly less overfitting, and deep kernel learning behaves the way you'd want it to behave. And I think he suggests using HMC. Well, HMC, if practical, of course, it's very expensive, but in practice, you can maybe use less expensive methods like stochastic gradient Langevin dynamics, which is essentially just SGD with some added Gaussian noise. And this seems to at least significantly mitigate overfitting in these like toy examples. I don't think you study sort of anything with CIFAR with this, but it seems like in principle, one would expect being fully Bayesian to help in this case. And the third technique, which is what I'll spend the remaining section of the talk discussing, is trying to explicitly prevent overfitting by regularizing the feature extractor in some way. And I'm going to mainly focus on 2 papers that explore this topic from sort of different angles, but they end up converging on similar techniques. So one is a paper from Google Research. It's the Leo et al. Paper. Actually, Shreyas Padi, Miguel's new student, is a co-author on this paper, although I don't think he's in the room at the moment. Maybe he's on the call. So if you're here, Shreyas, feel free to comment on this. And then the second is one from Yaron Gal's group, this Van Amers et al. So I took an illustration here from the Van Amersfoort et al. Paper because I thought it really nicely illustrated the problem that both these papers seek to solve via regularization. So the problem that they identified, they call feature collapse, which is that the feature extractor might not respect distances in the input space and therefore can make overly confident predictions about points far away from the training set. This seems to match what we saw in this 1D toy example from Sebastian's paper. And they really nicely illustrated actually here. So here they just have a really simple 2D classification data set where you have two clusters, and obviously you're trying to classify which point belongs in which cluster. And most of the points in the space just do not lie in the data manifold. So they do some deep kernel learning on this toy data set. And what they find is that the feature extractor, which they've also extracted into a 2D space, seems to have compressed the data set, or it's compressed the whole space rather, onto like a 1D manifold. And then you see this point here represented by a star, which is really off manifold and quite far away from the points, ends up actually being mapped onto the same location as one of the clusters. And therefore, you'd expect that when come time to make predictions, it would very confidently predict that point as being part of one of the clusters with very little uncertainty, despite, of course, it being actually quite far away, and you would hope that it would be very uncertain. So how would you mitigate this? One strategy that was first proposed in Liu et al., although I think that was proposed originally in another context for GANs or something, but one solution that was proposed is to make sure that the feature extractor is by Lipschitz. For those of you who haven't heard of this by Lipschitz condition, I think it's pretty simple to explain. It just means that there's two constants, L1 and L2, such that for all pairs of points, x1 and x2, in your data space, you have the following set of two inequalities, that L1 times the distance between x1 and x2 under some norm in your input space, obviously that would depend on what your input space is going to be bounded by the distance between these 2 points in the feature space, which is then itself bounded by some constant L2 times the distance in output space. Let me explain why this is intuitively why you should expect this to be a good thing to have. So the first inequality here suggests that if 2 points are close in feature space, then they must necessarily be close in input space. So as you can see from the, I guess, thinking about the previous example again, you have the point with the star and these green points, which are very close in feature space, but actually they're quite far away in input space. So that's an obvious violation of this first inequality here. And the second inequality is the opposite thing, that if 2 points are close in input space, then they also must necessarily be close in feature space. That wasn't really illustrated as being a problem on the previous slide, but you could imagine that this could occur, and that having this condition also be satisfied would then prevent this from occurring. And this would be another failure mode that's avoided. Although I don't actually know if there's any situations I've seen for being underconfident. Sebastian, do you remember any?
No.
Okay, well, regardless, it's a nice thing to have. It's like, at the very least, it provides you with a good guarantee, and will hopefully make you more confident in the behavior. I think so how did they achieve this by Lipschitz condition? It's maybe not, it's obvious maybe that you could test it in practice, but maybe not obvious how you could guarantee it. And the way that they, I think in both these papers choose to do this is by something called the spectral norm, which is just that based on some theorem that if you use a resonant architecture and you regularize the spectral norm of the matrices, which is like a norm based on the singular values, I believe, the details are not super important, that this ends up guaranteeing that your network will be by Lipschitz with some constants. And I think the first paper just regularizes the matrices, and the second paper regularizes that plus the batch norm, which has like a very strange Lipschitz constant, but they sort of make it work a little bit better. In practice, they find that this really effectively seems to solve the problem. So if you look then at the full figure here, we have it in the input space, the original deep kernel learning with this feature collapse, as they so call it. And then if they instead use this by Lipschitz network, then you end up with a much more meaningful feature space where you see that the star is quite far from the two clusters, and the two clusters are still quite nicely separated. And in fact, you can really see how it's just sort of a rotation and distortion of the original space, but it's not in any way violating the Lipschitz conditions. Now, in practice, this also means that the outer distribution predictions are going to be better because it's respecting the distance. So it sort of fixes this problem. And then they have a ton of results showing that it also helps in things like UCI and CFAR with both accuracy and calibration, which is sort of what you'd hope. Andrew, so
it seems to me like the metric is really important here.
I would agree.
The thing. So like how we did our recommend this?
I think the metrics they used was just the L2 norm, which is obviously not the greatest metric for images. Do you remember actually, Sebastian?
Sorry, which metric?
So the metric
So
in
in
input
the
space.
Lipschitz condition, you need to define a metric on the input space, or like a norm on the input space or something. I mean, a norm on the input space, and that seems really crucial because that sort of defines what is close and what is far away from the purpose of uncertainty. And if you go back to something very simple like sum of squared errors on images, that kind of feels like you're throwing out the potential gains of using a big feature extractor in the first place.
Yeah, I don't really know what we need to do.
Yeah, I mean, I totally agree with you that the metric is going to matter. And like one of the downsides of these like simple illustrations is that there's a very natural metric here that L1, L2, they're all kind of going to be very similar in this, and you can't really, they're all probably going to have good behavior. Whereas if you go to a really high dimensional space like images, it's actually really going to matter which metric you use, and that you're not going to get this nice behavior no matter what you choose. I think what they argue is that at the very least, if it's close to L2 space, that's like better than nothing. But I think that this would probably be much more powerful if you use a better metric. Now, this method that they actually use, this spectral norm, I think that only works for, like, that's certainly not going to work for any metric. I think it's just going to work for L2, but I'd have to double check. So this is like a very specific case where you can ensure this by Lipschitz condition with some particular norm, with also this particular architecture. So it's not a very general thing. But I still think, suppose that you do have a metric X that you think is reasonably good, then having this by Lipschitz condition would still be beneficial. Although again, for high dimensional images, finding such a metric is itself a really challenging problem. So maybe you're just sort of pushing the difficult part to somewhere else, and then that's not super helpful. But yeah, I think, and this is maybe a sign that I think that the field of deep kernel learning is like still maturing. Like there's a lot of these like kind of obvious things or like difficulties that I think have yet to be properly addressed. But I think it's like slowly moving forward, and there's a potential. I think actually that's a, oh, sorry.
Could I ask a question regarding to the previous slide?
Yes.
So in the paper, is there any discussion on how this constraint in the feature space translates back to say regularization from the weight space? I mean, this looks like a function space regularizer. Is there any discussion on say what form of prior should we use for the weights that could produce similar regularization effect?
I don't recall there being any discussion. I think they were doing this in a fully frequentist context. They were just getting a point estimate for the weights of the neural network. Could you do the same thing with good priors? I don't see a reason why not. But I think they were doing it again in a fully frequentist context. So in every step, they would do a gradient step, and then they would do this step to, I guess, bound the spectral norm of the weight matrices. And I think estimating the spectral norm itself is a bit difficult. So it's sort of another iterative procedure. And then they ensure the spectral norm is below some threshold, and then they proceed with the next gradient step. Does that sort of answer your question?
Yes, just want to clarify a little bit. So for the weight space, we are not necessarily doing Bayesian inference. We could put some regularizer like L2 norm on the weights. So yeah.
Yeah, and I think actually a lot of people in practice, they do use weight decay, which is basically like doing map instead of maximum likelihood.
Yeah.
That's just one of the tricks that people seem to use. Actually, Sebastian, having played around with this, do you know if that tends to make a huge difference in practice? Or is it just different?
Weight decay really like does nothing because it basically just shrinks the features, and you can just shrink the length scales accordingly.
That makes sense. Especially for like a ResNet, which is a whole neural network, is like, I guess, invariant to the scale of the weights, at least for predictions. I guess not for length scale, but you can always just use the length scales too.
Yeah. Yeah, the length scales end up just counteracting that.
Yeah.
Happens in the features of just plain weight decay, which is why this sort of more complicated regularization is necessary.
Yeah.
Can people hear that? Okay.
Do you want to again?
Oh yeah. Sorry. Did everyone hear Sebastian? Okay. You can repeat that.
Should I go?
Yeah.
Yeah. So with just standard like L2 regularization, what happens is that the lengths, it basically just kind of shrinks the features you get, and so the length scales for the GP just kind of shrink accordingly to counteract that. So you can try to regularize then the length scales as well, but then you've kind of got to strike the balance right between, like it's very tricky to get a good regularization on the length scales that will like not completely over regularize it as well.
You actually love the length scale? It's not fixed?
Sorry?
Can you just fix the length scale?
You could, but then that's essentially also like there's a risk then if you put too high of a weight decay, like that'll be bad too.
Yeah, I didn't mention this in this. In general, are you actually learn? I'm surprised.
In general, you do learn the length scales. Yeah.
Does that help then? Doesn't the feature extractor just back everything to the right? Like, it seems like it's degenerate.
Well, I guess it depends a lot on the initialization, because once you've got pre-training as well, and then as it's very unstable to train, so you do need a good initialization for it. So I think learning the length scales might help it to find that.
One thing to note, I think, is they're always using ARD, so there's multiple length scales, so it's learning like a separate, essentially, importance for each feature, which I think is helpful. If it was a global length scale, I would totally agree, but I think that learning a relative importance of different features is
that
beneficial.
sounds risky if you're using SVI. It sounds like SVI will improve then and get rid of, like you're using DI. You would then over-improve it and get rid of a bunch of features that should be. One of my mental models of what's going on is that the SVI has a tendency, or VI has a tendency to underfit, which plays quite well with the overfitting of having this big parametric component to your model. And so the reason why SVI maybe helps a little bit is those two things cancel out a bit.
Yeah, I would probably agree with that. Although I haven't done any experiments directly to look at the effect of SVI, because I mean, obviously then you get into more issues with like how like the initialization matters even more, and training it becomes trickier and stuff. So it's hard to come up with anything conclusive about.
So I had a related question, which is, have you thought about, or people thought about just using different subsets of data to train the feature extractor from, say, GP hypers? So you just don't touch the stuff which you're learning in the GP hypers, you don't touch with the feature extractor and vice versa. It's like almost like using highlight sets to train one versus the other. You could flip flop backwards and forwards between the two.
Yeah, I haven't seen that. That's quite interesting.
You've got tons of data, which I guess some of the you're heading towards that would be totally acceptable, I think.
Yeah. No, that would be an interesting thing to look at, maybe.
Yeah, I mean, in a sense, that's like it's a little bit similar to like the use of mini batching, where you're only training on a small subset of the data each time. But this is like a more, I guess, it's a non-random split, or like it's not sort of random for each step. It's like a specific set for training that GP hyperparameters and a specific set for the feature extractor.
Yeah, so they're never talking to each other.
Yeah.
They don't get to collude on the same data. Explain it to you.
Very, very similar point. It sounds like an obvious thing that someone would have tried is like take a neural net, retrain an image net, and then like replace the final layer linear with like a phase linear regression on GP or something. Has that been tried?
I don't know. I don't think so off the top of my head, but I mean, that's essentially like, I think the overfitting really comes in when you try to jointly train everything, which is essentially what Rich was saying earlier. So I mean, that has been tried insofar as pre-training on the same data set and then keeping the neural network fixed. But no, I haven't seen anyone take, the whatever you can download from PyTorch trained on ImageNet.
Yeah, I think as you talked about yesterday, like one of the potential issues with that could just be the high number of classes in ImageNet. But it's like not
ImageNet is tricky. I haven't seen anyone do deep kernel learning on ImageNet. I think because there are issues with the number of inducing points you would need for that would be quite large with the number of classes it has. But
maybe people have tried it and it just didn't work out well, so they didn't publish it. Maybe no one's tried it because it's, I don't know, computationally intensive.
Yeah.
So you could do stuff like, take 100 classes or something like that, and you just retrain it back home and as a surrogate place to start. Probably okay.
Yeah, sure. Yeah.
That was going to be the other thing. Are you guys Is it fine to have a discussion now?
Yeah, we're wrapping up.
So the other thing I was going to say is, you know, what is the goal? Like,
Actually, do you want to come up here, Rich, so that everyone?
Should I just turn my mic on?
That might have some reverberation effects. Well,
we'll see whether. Okay, it's coming out of the machine. Yeah, that's not good.
Solid prediction there.
Yeah.
Okay, I'll come up.
Yeah, you come up. You can either come up here or you can turn the camera to face you.
Yeah, so I was just going to say, what's the goal? Like, what are we actually trying to do with these models? What kind of types of data set? Are we really going after computer vision? Are we going after like richly structured but quite numerous like regression data sets? And what kind of problems? Because, you know, classification accuracy, we're not really going to improve, or regression accuracy, we're probably not really going to improve. OOD is kind of interesting, but, you know, we're not really using any of the covariance properties really of the GPs, or using them to a very limited extent. So surely it's things like active learning and things which require dependencies across the input space, you know, sort of fundamentally is what we should be looking at. So yeah, what's the killer app?
I think for me, the main hope for deep kernel learning methods would be like high dimensional, very structured data, things where we know that GPs struggle because there just aren't very good kernels for them. And so I guess like that would be my hope. You know, I haven't seen any like convolutional GP or convolutional deep GP that gets close to the accuracies you're getting with deep kernel learning. So that in one sense, that's sort of what I would hope could be achieved. But I think it is a good.
We've already got methods for doing that. So like, what's the?
Well, to have the uncertainty kind of hopefully guarantees, or whether they're guarantees or not, whatever. But like, you know, the uncertainty properties that a GP gives you.
Yeah. Okay, on the microphone.
Yeah.
I sort of think there's an elephant in the room here, which is that we don't really know how to combine covariance functions or kernels with a lot of parameters with learning. We don't know how to get the benefits of doing the Gaussian process thing that sort of automatically gives the right error bar. We don't know how to map that onto architectures that has a lot of parameters, right? So I guess I was guilty of being one of the authors of the manifold Gaussian process paper, which I think is a failure in a way, right? Because it doesn't tell us how to train this thing. I think we genuinely don't know how to train it, right? I really dislike a lot of the approaches that are being formulated in literature, where people say, oh, if we sort of use this sort of fairly broken way of optimizing this thing, then it doesn't go badly as so much. Like, you know, I think that, you know, that's not the solution to the problem. I might empirically might do a little bit better, but it's not because it's a real solution, right? So, you know, I think we simply don't know what's the right way to look at this. And I think maybe, as Rich suggested before, maybe going back to ideas based on cross-validation, where you have a guarantee that you can't overfit because it's structurally built into this thing. You know, maybe that's a way to try and address this problem. But I think, you know, many of the approaches, you know, are not a sort of non-solutions, right? They can get rid of the very worst of the behaviors, right? It's not because it's really fundamentally saying that, you know, this is a way to solve the problem. But this is a personal view. But yeah, so I'm a little disheartened by this literature.
Actually, could I ask a question here?
Yeah, of course.
So in this talk, it's mostly focusing on learning the kernels, but there is also a very large family of methods based on weakly trained kernels, basically neurotangent kernels, NGP kernels, where the parameters in the kernel are not trained. We just compute the kernel, which is equivalent with a probabilistic neural network, and then add a GP layer on top of that kernel. How do we compare, I mean, these two paradigms of kernel learning? I mean, in one paradigm, it is easier to inject the bias that we found useful in deep learning, like average polling, like ConvNet architecture, like ReLU activation. And it has been found in several papers that injecting these inductive bias into the kernel actually significantly improve the performance of the GP model without learning the kernel.
was a lot of details in that question. I'm not sure I can answer that completely on the fly. I mean, I think if you do treat parameters of neural networks in a probabilistic way, then perhaps that is a proper solution. The question is whether you can really make that practical. And maybe there are some tricks of doing this in lower dimensional projections, and the ideas along those lines. Maybe that'll work. I think maybe we should take it offline. The discussion about the individual methods become very technical.
I like that suggestion. So this is actually a really good kind of segue sort of into the into the conclusions. Maybe that's slightly at odds with what we've just said in the discussion. I still think that deep kernel learning can be viewed as at least promising, if hasn't maybe delivered, but it could potentially deliver as a way to combine neural nets and GPs. Maybe actually give sort of my answer to Rich's question about what would be the killer application. I would hope it would be something like active learning or optimization on like structured data, like maybe something like good and like compete with BNNs and things like good classification accuracies with decent uncertainties. Like I think BNNs are definitely in a much better state than any deep kernel methods. Maybe deep kernel could improve, maybe not, but that's sort of like I think that the game that's being played here somehow getting like, I mean, versus I guess like the other avenue to get GPs to work really well on this, which is like designing sort of these very complicated like convolutional kernels or things like this, which from my understanding they haven't just reached the accuracy that's competitive with neural networks at all. Like you could maybe take you're not going to take a 20 or 30% accuracy drop to use a GP, whereas maybe with deep kernel learning you could have a minimal accuracy drop, but then also get the uncertainty benefits of a GP. At the very least, I think it's possible that this could work out, but of course there are a lot of fundamental issues, especially if you're using empirical based hyperparameters. I mean, so far it seems like there's like a sort of accidental implicit solution if you regularize it via mini batch training, and this seems to make the overfitting less severe than it could be. Like this by Lipschitz property, I think is an interesting idea to explicitly regularize the problem. Of course, the problem is actually what Andrew pointed out, which is that you need a good metric for this to work. And in practice, we don't really know that for high dimensional images. I mean, if we had a good metric, then we could just sort of maybe make the kernel directly with that metric, and then we wouldn't really need to worry about this whole thing. And then, of course, one solution that's out there is to just do fully Bayesian inference. But that sort of says that, well, if we solve BNNs as a subproblem, then we can stick the BNN into this thing and be even better. But that's maybe getting a little bit carried away. If you have a good BNN, maybe you can just use the BNN. But of course, maybe the GP would be slightly better than a BNN. You don't really know. One thing I wanted to point out is that there's still no ImageNet experiments to my knowledge and Sebastian's knowledge. And again, you can interpret this different ways. Maybe it's been tried, didn't work so well. Maybe it's just sort of difficulties of scaling it. Maybe it's just not competitive with like other methods like BNNs. It's not really clear. So let's then actually, this is sort of a segue maybe into continuing the discussion we were having earlier. What do we see as the future of this field? I think Sebastian and I are in agreement that deep kernel learning is a way at least to improve GP performance for image data compared to very complex sort of custom kernel designs, which are either just don't get good accuracy, or the kernel computation itself is actually quite expensive, whereas this is like relatively cheap, works fast, works with stochastic approximations, and it seems to like bring the accuracy on things like Cipher up to an acceptable level. I think it's really interesting to again highlight this contrast with BNNs. I sort of see deep kernel learning and BNNs as kind of playing the same game. They're both ways of somehow getting neural networks to give uncertainty estimates. One is by actually being uncertain over the neural network itself, and the other is by sticking the neural network into a non-parametric model, which will give you uncertainty estimates. I guess if you want to be exact with DKL, you can get these exact uncertainty, even though, of course, it might not be very good in O(n) cubed, so it doesn't really scale that very well. With BNNs, if you get exact uncertainty via, it's like exact sampling, that takes some unknown amount of time, depending on how good your MC technique is or whatnot. It might in practice be similar or longer to n cubed for some reasonable sized data set where, I mean, of course, both are really intractable in practice. When you're doing approximate inference, we have decent GP approximations with inducing points, although as Sebastian pointed out, if you have something like 1,000 classes for ImageNet, you actually need quite a few inducing points. Maybe this becomes not so practical. With BNNs, of course, people in this group are familiar that there's many different approximations for BNNs. All of them have their strengths and their weaknesses. Some are more expensive and more accurate, some are less expensive, less accurate. And of course, like, if you're interested in things like calibration or uncertainty, generally, like the more approximate you are, I think the worse these metrics become. So there's a trade-off, and I think it's a similar trade-off with DKL and BNNs. I think with, like, in particular, particularly focusing on overfitting, with DKL, we have this problem where you can really overfit. There's some sort of very highly peaked mode of theta. With BNNs, we have a typo there. A lot of methods are going to focus a lot on a single mode. Maybe this also causes them to underestimate uncertainty, although probably not as severely as with like the 1D toy examples where it really underestimated uncertainty. But it seems that in general, could be something that you might call overfitting to like a particular mode, and that you would therefore underestimate uncertainty. Although from what I've seen, it looks like it's much more severe in deep kernel learning than Bayesian neural networks. But I thought it was an interesting point where maybe being a bit similar. And then, yeah, of course, like I said earlier, that BNN could be a part of a deep kernel learning. If we solve BNNs in some way or have great BNNs, then this might also give us great deep kernels. Whether or not that's useful remains to be seen. And just final thoughts on some downstream uses. I think one interesting thing about kernel methods in general is that they have good interpretability, because at least for, say, regression, your prediction is just going to be a weighted sum of your training data points, and therefore you can directly attribute predictions to your training points, and that's like a nice feature to have. There's a lot of work, some in this group, a lot outside of this group, about interpretability for neural networks. With a parametric model, you have to somehow interpret your parameters of why they're giving you some predictions. At the very least, if you have a deep kernel method, then you can directly attribute the predictions to the training points. Of course, then you may pose the question like, why, it says that this training point was very impactful because it's very similar. Why are these similar? And then that's just that the answer is just they have similar features. So then you sort of bottom out at the same neural network interpretability questions, but at the very least for the surface level like predictions, you can at least have a good interpretation that's like pretty easy. I think that's a nice thing. I think it might be really interesting to look at this for few-shot learning. So GPs just generally work well with small numbers of data points. Neural networks generally don't unless you regularize them quite heavily or Bayesian or something like that. So potentially, like using neural network features and then combining them with GPs could be a way to get few-shot learning to work reasonably well. And I think actually in this Bradshaw paper, which was actually by John Bradshaw, who's just left this group earlier this year, said I think he showed some promising results for adversarial robustness, although these results are quite out of date. But I at least think it's an interesting thing to consider. Same with BNNs. The more Bayesian you can be, the more uncertainty. This could potentially contribute to making adversarial robustness a bit better. And that was, I think, all I had to say about this. For perspective, and that essentially concludes the reading group. So maybe it's time for questions and discussion.
I think your point of that feature learning must be a way forward. So what worries me about BNN literature and this literature is it becomes decoupled from current practice in, say, computer vision, if that really is the target.
Do you want to come up here?
Sorry?
Do you want to come up here if you're going to say it?
Yeah, well, I'm hoping that people can hear from that.
Yeah, I'm sure so.
Yeah, so I'm worried that, for the BNN literature and the deep kernel learning literature, we're sort of like comparing within the sphere of like deep probabilistic methods, and that's not really ever going to have any impact on people in, say, computer vision, if that's the target audience, because they're running off in situations where ImageNet is now small, and we're still sort of fooling around with CFAR 100 and things like that. And so I think it would be really worthwhile trying to make a step towards doing stuff at scale. I mean, it's not the only research to do, but I think it would be sort of important. And maybe, not being as principled, so doing something fairly heuristic. And probably the application which stands out is active learning in a few-shot setting using a pre-trained backbone on ImageNet or something like that. So take a new data set which it's not seen before. Take the pre-trained backbone off ImageNet and now use the GP to do active learning in that space. And maybe it's like it's a few shot learning thing, at least to start with a fairly modest number of classes, and compare, like seriously compare to the heuristic baselines that the deep learners use. And if it's out of distribution and do and distribution, but again, there are lots of sensible heuristics that they've thought of. I think that the danger is we end up just moving too incrementally and too slowly, that we're never going to bridge the gap to a serious computer vision application, and run off the distance and we'll be left behind. So I think we sort of, at least part of it should be trying to seriously take on a task and do the best we can with current tech at scale.